Okay, good morning. Let's get started. I'm going to introduce Marcella Carena, who is a physicist at Fermilab at University of Chicago, and she's going to tell us about the physics landscape. I know we're starting a little late, but Marcella always finishes early anyway. So, Marcella, go ahead.
I listened some laughs there. Okay, good morning. It's a pleasure for me to be here, even at 8 a.m. And I see we are all ready for these last 2 days of SNOMAS. It has been a very intense, but I think very productive meeting so far. So I was asked by Joel to give a very brief introduction of our panel today, that will be science highlights, frontier summaries and panel discussions. So I will very closely follow Joel's guidance in my very brief introduction, and then we will go to the frontier physics highlights that will be presented by the 5 corresponding conveners, and then we'll have the last half hour hopefully for discussions and questions from the audience. So let me start, or not. Okay, so the standard model is very successful and explains things, many things extremely well. However, of the 5% that the standard model, of the 5% of our universe that we have a very good theory for, namely the standard model, there are still a lot of things that are open questions. And I think one of the most important ones is why electroasymmetry breaking occurs. We know it occurs, but we don't know why. In fact, in the standard model, we put it by hand, electroasymmetry breaking, so we get what we put in. And related to that is what is the history of the electron-weak phase transition. And then, of course, is what is behind the reason of the hierarchy in fermion masses and their flavor structure. Then there is a second tier of unknowns that belong to different sectors, may belong to different sectors, and may have their own constituents and their own laws. And this is the nature of dark matter, the origin of the matter-antimatter asymmetry, and the generation of neutrino masses. And finally, we have here very fundamental questions of particle physics that we need to answer. And they are difficult, like the cause of the universe accelerated expansion, we call it dark energy. What are the quantum properties of gravity, and what caused cosmic inflation after the Big Bang? So the standard model is silent about all the above, and beyond the standard model physics is at the core of it all. Each of the frontiers that we will listen to their highlights today aims at deciphering many of these mysteries, and their approaches are in many ways complementary to each other. So I will now take these 3 examples to show you how the 5 frontiers we are going to listen about today can chime in these points. So let me start with the sample of dark matter, beyond the standard model example of dark matter. So the theory frontier, aims at which are possible dark matter candidates, possible associated dark matter sectors, and of course, what are the corresponding experimental signatures. The cosmic frontier asks how can we refine our understanding of the properties of dark matter from cosmic observations. For example, through does it have self-interactions, or when we look at direct detection or indirect detection, how are the interactions of dark matter with the standard model particles? In the energy frontier, the question is, can we produce and infer the presence of potential dark matter or other dark sector particles at the LHC? The neutrino frontier, thinking about dark matter, thinks, are there sterile neutrinos? And if they are, can they be the dark matter candidate? And for example, are there sector effects already affecting neutrino experiments? In fact, for example, one can think about a dark neutrino with a dark set prime, a dark force that could actually accommodate the Khabibo anomaly. Okay, so then for rare and precision frontier, This is a bit farther stretch, but in fact, if you think about models that have new physics and BSM theories of dark matter at the TeV scale, they usually come with flavor violation effects. And so in the rare and precision frontier, we will see this effect somewhere. So this is example number one. Example number two, dear to my heart, is the matter-antimatter asymmetry. And here, what does the theory frontier ask is which are viable models of baryogenesis or leptogenesis, and what do they imply for experiments? From the side of the cosmic frontier, we can ask, for example, so this is not an exhaustive list, this is an example of all the things we can ask. Can we find gravitational wave signals from early universe first order phase transitions? If we think about the energy frontier, thinking about matter-antimatter asymmetry, the question would be, can we discover an extended Higgs sector that points towards electron baryogenesis? In reality, an extended Higgs sector could help in making the first order phase transition sufficiently strong, as is not in the standard model, and also bring new CP violating phases that are necessary for baryogenesis. Or there are other type of models, one is dear to my heart because I work on it. Can we prove models of new gauge forces and dark sectors, basically where CP violations is in the dark sector, and this is a way to evade very strong EDM bounds, or our beloved and always alive supersymmetry, and these models would also allow electron baryogenesis. Energy frontier will say, we have a lot to say to these models. Then, if we think about neutrino physics frontier, the question is there leptonic CP violation, and what is the implication for leptogenesis models of this leptonic CP violation? Of course, models of leptogenesis would also vary depending what is the mass hierarchy and if neutrinos are Majorana or not. So learning that would also kind of help us understanding which models would be viable models of leptogenesis. And if we think about rare and precision frontiers, could be, can we detect EDM electric dipole moments induced by the new CP violation phases that are required by electron baryogenesis? In fact, is a tension there because we need sufficient CP violation to generate the baryon number asymmetry, and EDMs are already constraining us to have a given amount of CP violation. Moving to the third example, this is neutrino mass generation, again, theory frontier, which are the viable models of neutrino mass generation and what do they imply for experiments. Cosmic frontier, we know from the cosmic frontier, we have the best bound on the sum of neutrino masses from cosmic observations. So the question is, can we improve on these bounds? Can we measure the sum of neutrino masses? The energy frontier, of course, this is a bit more of a stretch, but in some maybe not the vanilla ones, but some extended models, CISO models of generation of neutrino masses, they are heavy neutral fermions that could be discovered at the LHC. And then neutrino physics frontier, of course, this is the core of it. What is the mass hierarchy around neutrinos, Dirac or Majorana? And for rare and precision frontier, it is natural to ask, is there charged lepton flavor violation, signaling a whole new sector related to the neutrinos as well. So I hope I convince you with these three examples that BSM is everywhere here, trying to solve these problems that are at the core of the things that we don't know, and that the 5 frontiers we are going to listen about today have a lot to say in this direction. So now I will not go through this whole menu. It's like when you go to the restaurant and you kind of go through the menu very fast. But I want to convey all what we have on our menu of possible discoveries and learning in the coming decade from current HEP program. Here we are to think about the future, but let's see what we have on our plates, possibly. So LHC, this is a list, not exhaustive, of the things that we can discover at LHC. I am, of course, excited about Higgs cousins of many types with many possible implications. Many possible implications means new scalars could help us understand electron symmetry breaking, could help stabilize the Higgs potential, because of the way they interact, they will change the running of the particle coupling, could be a source of CP violation and could give us a strong first order phase transition for electron baryogenesis and even more. Of course, then we can have discover or infer dark matter and discover some dark sectors, field interacting particles, long-lived particles. A lot has been done in this direction in the past years. There could be new forces, new kind of scalars or fermions, leptoquarks. We could learn if the Higgs boson is composite or not. We can learn about flavor violation and CP violation. And we can, of course, have lepton flavor violating signals, even if the ones that we were very much hoping may be diluting. Of course, like in any menu, you get the little footnotes that says, you know, good for no gluten-free or vegan or whatever. So here is some items of all this list may be related to the mu(G)-2 result from Fermilab. Of course, other accelerator-based, non-collider, but accelerator-based experiments will add uniquely to this list. If we move to neutrinos, I will be shorter here, but the short baseline neutrino program will have results that can make a definite statement about the mini-Boone anomaly and possible beyond standard model interpretations. Of course, there are many anomalies in the neutrino sector, and other current anomalies could be resolved or confirmed. We will learn something about the Mars ordering from global feeds, but a definite result would only be possible if we are able to change this tension to clarify this. And if, sorry, you distracted me, Joel. But a definite result would only be possible if we are able to resolve the tension that is now between NOVA and T2K results and so on. And of course, CP violation will still be uncertain and we'll have to wait for Dune or beyond. Rare and flavor, we know that we can say something about charged lepton flavor violation, hopefully mu2e, lepton number violation, neutrino-less double beta decay, and maybe we can have quark flavor opportunities in the horizon. If we go to dark matter, direct dark matter searches could discover one or more kind of dark matter particles. As we know, there is a very full and very slate of dark matter new initiatives for light dark matter that will become mature, and then we may have discoveries. And there will be all these fixed target accelerator based experiments. Some are neutrino experiments, some others that may have also discoveries. Again, here, our footnote is that a discovery in any of these possible experiments that are and cosmic probes would have immediate implications to the other experiments. So a question is, are we ready for a discovery? Each of us, with the, where our hands are in all these possibilities of experiments, are we ready? And this is going to apply for dark matter and other sectors as well. And finally, in the cosmic frontier, there is a big plate here, or a very full plate. So there are unique probes of dark matter properties with interactions of the standard model with itself, as I mentioned before. We will have even better limits or measure the sum of neutrino masses from cosmic probes. We will be able to say something, hopefully, about dark energy being dynamical or not, about primordial BMOs, either observed or better constrained. We will be able to hopefully resolve the Hubble tension, and this may be an indication of physics beyond the standard model. Here we can have a handle beyond, so better measurement of an effective for light relics. So if we have light weakly interacting particles that may be not accessible in terrestrial experiments. And last but not least, gravitational waves would be there as a window to early phase transitions. So I hope I convince you that we are in the 5-star Michelin restaurant, and that we have so many exciting things to come. So to conclude, two slides that I want to say: the growing importance of cross-cutting activities. With my big theory hat here, theory is a cross-cutting area that integrates into everything we do in HEP. I see theory as the glue with experiment, with computational efforts, with machine learning and quantum science. Theory is very important. This is also true, so this cross-cutting is also true for instrumentation and computation, and this will be summarized in the next panel And you will see a lot of great pictures. We have decided with Ian, I have 0 pictures, he gets all the pictures. So that's the division we decided among the moderators. More recently, AI and machine learning has begun to assume a similar role in this cross-cutting area, being a cross-cutting activity, and quantum science shows similar promises as we heard in the sessions before. So finally, my last a few observations, I would say we are proving many of the deepest secrets of our universe. HEP is a very exciting field with a strong program as recognized by our stakeholders and other communities. I think the HEP program, as I hope I tried to convey to you in these few minutes, is broad by design, both to maximize discoveries and to make the science connections that we will need to make in order to make sense out of those discoveries. So with so much discovery potential in the coming decade, we are planning for success. We are being very ambitious, but also realistic about timescales. And an exciting field, which I hope with multiple Nobel Prize worthy discoveries, is going to provide momentum to launch many new initiatives. So I would say we have done great advancements since SNOMAS 2013, and we are ready to move into the next P5 exercise. And now, without further ado, we are going to listen to the frontier physics highlights from Cosmic, from Cosmic Frontier, Energy Frontier, Neutrino Physics Frontier, Rare Processes and Precision Measurement Frontier, and Theory Frontier. They will do a summary of the physics highlights, a summary on experiments proposed to investigate them, comment on what each frontier science of each frontiers on the current P5 science driver. And I hope that then we all together will discuss if the collective physics highlights from all frontiers reaffirm what we have as P5 physics drivers, or if we need to extend them and how. Thank you. So now I guess we need to connect with Tim.
I'm here. I can share my screen if you prefer me to do it that way.
Okay, so.
But you'll have to stop sharing on that side.
1 second, Tim. I know you want to be the big head. You are the big head. So can you share the screen?
Yep. I think you can probably see my slides now. Is that right?
Yes, perfect.
And as you see, I asked that maybe the captions could go in a particular place. With apologies to Jesse Thaler, I've made this bigger, and let's see if it actually works this time. Should I start?
Yes, you can start.
Please go ahead, Tim.
Okay, thanks. So it's a pleasure to be speaking to you today. I have to say it's been really wonderful to actually be with you in person for the last 10 days. And it's too bad that I couldn't actually be there to continue that for today. But I'll give you some of the science highlights from the Cosmic Frontier. So starting with the highlights themselves, as we said at the beginning, the Cosmic Frontier seeks to understand the fundamental physics that governs the behavior of the universe and its constituents. It's a broad program that encompasses many different kinds of scientific activity. I've split this up into a few different categories. So we're going to start with dark matter. Marcella just introduced the subject. The space of dark matter models encompasses a dizzying array of possibilities representing many orders of mass and coupling. The Venn diagram is something that we saw in SNOMAS 2013. It was prepared by me for that exercise, and it showed our kind of how we were arranging theories at the time. Might also be abstract art. What we've done in this SNOMAS, and as Aaron showed us on Thursday, is to try to condense these models into something of a dark matter cartoon, where on the x-axis we've got the mass of the dark matter spanning its many orders of magnitude, and the y-axis we have interaction strength with strong interactions like in the standard model at the top, and very weak interactions including gravity down at the bottom. And you can see that these models pick out some sort of very interesting targets that we're interested in for other reasons. This is a very difficult problem just because of its breadth, but we have a plan. And if we had to summarize that plan, it would say something like delve deep, search wide. We employ a range of direct searches for WIMPs interacting with targets on Earth, indirect searches for annihilation products, and cosmic probes based on structure to scrutinize priority targets such as WIMPs and QCD axions, while broadly scanning parameter space, leaving no stone unturned. You can see here a snapshot of what that looks like today, with major inroads made to the priority targets of the WIMP and QCD axion, and a lot of progress made for sterile neutrinos. That's largely based on cosmic probes because they typically appear as warm dark matter. But of course, there's still a lot of parameter space, including a lot of high priority parameter space that is left to go. The next 10 years, including future generation 3 direct searches for WIMPs and axions, combined with future indirect observatories, a program of smaller scale experiments, and key inputs from cosmic probes results in very broad coverage, where, of course, we can't cover the entire parameter space, but we really managed to cover most of the priority targets, or maybe even all of them, and a lot of other territory as well. And of course, it's worth mentioning that these giant advances in coverage mean that it's not just that we're going to rule out a lot of parameter space, we have a lot of room for transformational discoveries. If you didn't get a chance to see Tracy or Risa's talks on Tuesday last week, I really suggest you look at the recording. These yellow stars show places where we could imagine actually a discovery coming just in the next few years. And any one of them, as Marcella pointed out, would be transformational for the rest of particle physics. Moving on to cosmological probes, it's a really great time for cosmological probes. And this is really thanks to the investments that were recommended by the previous P5. They have ensured that the next decade is going to be something of a golden age for cosmological data, able to inform us about the deepest mysteries of fundamental physics. And this is through probes such as measuring the cosmic expansion history, the CMB, growth of structure, and gravitational waves. And here are some of the observatories that are either taking data, finishing their construction, or that we intend to invest in the near future. So current observations, as Marcella showed us on Thursday in her presentation, have revealed key properties of the universe and its fundamental constituents, but there's still a lot left for us to learn. So this is kind of a snapshot. It uses a language that's not totally familiar to us, but these map onto onto quantities that we find very familiar, such as, for example, the energy scale at which the inflationary dynamics takes place, the dynamics of inflation itself, and whether there is actually scattering going on as it's taking place. The number of light degrees of freedom that were in thermal contact with the universe, but are too weakly interacting for us to know about them based on our terrestrial experiments, and so forth. If I had to summarize the approach here, the strategy would be something like search wide, aim high. The near-term future will be collecting data from DAISY, which has just come online, completing and executing Rubin LSST, and constructing CMBS4, which is currently on track with CD0. You may have heard that it's actually undergoing some redesign. This is actually something that is normal for CD0, and that we anticipate will result in a vibrant program that will look very similar to what we've been talking about all along. As a program, it will make unparalleled progress towards understanding the dynamics of cosmic inflation and also searching for new physics. As you can see by the progress made in some of these key observables that we mentioned just a moment ago. Longer term priorities are also something we have to start planning for in the next decade. This includes a roadmap to a future stage 5 spectroscopic facility and small projects and pathfinders towards new opportunities such as gravitational waves, 21 centimeter observations, and line intensity mapping. And you can see how these really get us down to the point where we can actually look at very exciting physics that we know, in some cases like inflation, has to be out there. So I was asked to talk about timelines. This is very complicated in the cosmic frontier because we have a lot of experiments. So I've got some graphical representations, and I really encourage you to look at the reports to get a more comprehensive picture. This is not even all of them. So in the CF7 report, you can find timelines for how we expect gravitational wave observatories to evolve, and also how multi-messenger astronomy will tell us about gravitational waves, photons, neutrinos, and cosmic rays. In terms of the cosmological surveys, I just mentioned DESI and Rubin, and the stage 5 spectroscopic survey, and of course CMBS4 is the immediate future in terms of starting a new project. You'll also see progress in the direct searches for dark matter, which currently are dominated by liquid noble searches, which will advance towards the generation 3 experiments in this timescale. And finally, but not at all least, there's great progress in searches for ultralight dark matter, such as axions or dark photons. And you can see here from the CF2 report, the timeline for making progress in that sector. Okay, and then I was asked to say a little bit about the science drivers and how they map onto the cosmic frontier. You can see that my version of the science drivers has the famous pentagon in the middle. So let's start with neutrino masses. Neutrino masses, of course, is a sign of physics beyond the standard model. It is of crucial importance for us to understand where they come from and what the dynamics responsible are. Here we've got two plots, one showing how upgrades to IceCube can actually give us unparalleled sensitivity to theta 2-3, one of the mixing parameters. And in her talk on Friday, Kate Schulberg showed us cosmic constraints on both light weakly interacting particles, including neutrinos, which maybe tell us something also about neutrino interactions, and also very importantly, the sum of the neutrino masses. So this is actually currently the best constraint we have on the sum of the neutrino masses, though of course it does come with some priors. And it's a very important player as we move forward in the neutrino program. So to summarize, cosmic frontier observations offer unique and important perspectives on the parameters that describe neutrino masses, and they can inform terrestrial searches. Second, identify the new physics of dark matter. Well, as we just saw, delve deep, search wide. Here's several plots that were produced by CF1 showing us different progress that we can make by looking at, say, dark matter annihilations, which are very effective actually at very heavy dark matter, and we'll be able to cover the entire thermal region in the near term. And direct searches targeting WIMPs, targeting lower mass MeV scale dark matter particles that scatter with electrons, and also in searching for axions where we can cover the entire QCD axion range. I think the most important message I want to add here is that the cosmic frontier is required to verify that any candidate particle we should discover in some other way is actually making up the dark matter we see, because it is only cosmic frontier that actually touches the dark matter that is all around us, rather than trying to produce it. Third, understand cosmic acceleration, dark energy, and inflation. So here are some examples of the beautiful measurements that we're seeing already from Marcelle in her talk on Thursday. There's interesting tensions in the data, which actually may be hints of new physics to come, though right now, I think we're still trying to fully understand them. And of course, we have great ambitions to finally understand the physics of inflation. You can see here how CMBS4 actually gives us sensitivity, which can distinguish different motivated models of inflation. And this is really something that is unique to the cosmic frontier. It can access this physics, which we think operates at very, very high energy scales. It can also, of course, search for ultra-weakly interacting particles. And that's actually shown here. The next driver is explore the unknown. I have to say, my reaction to this is, where do I even begin? Because there is just so much to talk about, including ultra high energy ordinary standard model particles, seeing them interact in regimes that are very difficult terrestrially, searching for light weakly interacting particles that are present in the universe, as we just mentioned, and using gravitational waves to study new physics, such as, for example, an early phase transition. And like I said, this is really just a very small peek into what is going on in the cosmic frontier in this particular aspect. So last but not least, we have the Higgs. The Higgs is not the go-to tool for discovering the cosmic frontier, but I was reminded that it has an important role to play. And also that this is still my favorite title of a paper that I've ever written. So to conclude, I think the slogan is delve deep, search wide, aim high. The cosmic frontier contributes unique opportunities to the pursuit of the 2014 science drivers. It has strong synergies with energy, neutrino, and rare processes frontiers. benefits from essential connections and with theory, where it also has synergistic activities, and computational, instrumentation, and underground facilities frontiers, and offers interesting opportunities for the community engagement frontier, which I think we should probably try to develop more. This is a beautiful graphic that was hot off the presses, made by Jesse Muir. It sort of summarizes much of our report in a graphical form. And finally, I just want to say thank you, and that's in particular, thank you, of course, to all of you for listening, but in particular to my CF co-conveners, topical working group leaders, liaisons, and contributors. The success of the Cosmic Frontier at SNOMAS 2021 would have been impossible without you.
Stay here so that I can show you the 5 minutes.
Good morning, everybody. So I'm here to present the physics vision of the energy frontier. Can everybody hear me? No, okay. So I'm here to present the physics vision of the energy frontier on behalf of the entire team, the conveners, my co-conveners, Minashi Narayan and Alessandro Tricoli, our topical group conveners that have been the pillars of our program and have pushed this through, and the entire community that have contributed at all levels and at all times during these 2 years. So just to introduce, so let's address directly P5 now and then. So the existing P5 drivers very much match the program that the Energy Frontier has developed during the years since P5, and in particular, the use of the Higgs boson as discovery of new physics, the exploration of the unknown, and the identification of the nature of dark matter through collider experiments. Now, compared to the last P5, we see that the energy frontier has developed a lot during these years, and we are at a sort of turning point because where it becomes clear then from what we know from the physics of the Large Hadron Colliders, that the region between 1 and 10 TeV is a crucial region to explore. And during this exercise, we have also had the high luminosity LHC becoming a reality. And that is extremely important as our base ground on which we build everything and we build our vision for the future. And during SNOMAS, the feeling of what is needed next has become clearer and clearer. In particular, the fact that we need machine to extend the potential of the high Lumi LHC, and we need to prepare and start the preparation for this machine as soon as possible, to keep the community alive, to keep the community engaged, and to answer the questions and the creativity of the new generations. We also think that P5 should consider new drivers, and in particular should consider how it enhances the physics that we do and the science that we do, have a diverse and inclusive community at all levels. A workforce that is diverse both in backgrounds, in expertise, in career levels. So the energy frontier is about the exploration of this scale, the TeV scale, the 1 to 10 TeV scale for what we can do so far. And it does that through a multitude of signatures and probes. At the core of our program stand the big questions that Marcella so nicely has summarized for us, and to which all of which we can answer in a way or the other through experiment at the energy frontier. And at the same time, we also explore the unknown, so things for which we cannot formulate the question because we don't know. So these are the two main goals in front of us. And we can do that using what we know, so the knowledge we have of electroweak and strong interactions, and also what we still are exploring, so exploration of what goes beyond what we know, what we call beyond the standard model physics. We remind that colliders have a unique opportunity to measure through same experiments a multitude of signatures, a multitude of possible probes and experiment and signatures. And this is really the strength of this program, because any signal of new physics that we get from anywhere will have to pass the test of colliders, and will have to be interpreted through the probes that we have at Collider Physics. So addressing the big question and the exploration of the unknown are really the goals, and we want to aim at them along two main avenues. One is the study of phenomena that we know, and the phenomena, so known phenomena at higher energies and with higher precision. And for these, also having indirect evidence of new physics. And for this, we need the factories of particles, of standard model particles, in particular factories of Higgs bosons. That is the particle that we least know within the standard model. And at the same time, of course, we want to push the energy frontier bound, and we want to go to higher energies, and we want to directly explore new physics. And for this, we need a multi-TeV to explore the multi-TeV scale directly, so multi-TeV machines. So these are the two main leads. Energy and precision is what we want to pursue for the future. And these machines that here we label as Higgs factories and future high energy colliders or multi-TeV colliders, very simplistically, pictorially can be seen as extending the program of extending the program of the LHC, including the high luminosity LHC, in two main directions in this world in which we only consider mass, scale, and couplings, either toward in the lower mass region that we arbitrarily put at around 1 TeV, through our weaker coupled theories, so more rare phenomena, and towards higher energies, pushing the bound up to 10 TeV for what is planned for the future. So the scenarios that we have considered are the one depicted here during this exercise, 2 years exercise, and we have been trying to listen to all the information that has come to us. You will hear much more tomorrow about the time frame of these machines and the technical characteristics of these machines in the second panel, in the third panel of this snow mass, so the first one of tomorrow. And just for your reference, these are summarized in two groups, the Higgs factory group and the multi-TeV collider groups with the time-standard information taken from the ATF report. So the physics, we see three very strong physics cases. One is the physics case of the high luminosity LHC. Based on LHC, on the extraordinary performance of the Large Hadron Collider, the projection for the high luminosity LHC in terms of Higgs boson precision measurements, Higgs boson exploration of the potential of the scalar sector of the standard model, exploration of theories beyond the standard model directly, as well as the richness that has come to this program by auxiliary programs that have been proposed during the last few years, make the case of the high luminosity LHC fundamental to think, and in particular the extrapolation for the high luminosity LHC, our base ground to think to the future. The next strong physics case is really pushing the Higgs boson precision program. It is crucial as the Higgs boson physics is related to all the fundamental questions that you have seen delineated this morning. It is the least and most mysterious sector of the standard model, and it is fundamentally related to understanding the origin of the electroweak symmetry breaking and the thermal history of the universe, down, 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 till the origin of flavor, from which we have a very interesting signals these days. Higgs factories will not only measure Higgs couplings at the sub-percent level and get the first bound and the first information about the Higgs potential, they will stress test the consistency of the standard model deeply. And they will also have direct access to low mass weak coupled beyond the standard model physics. So an extremely rich program we cannot move ahead without. During the 2 years of the snow mass exercise, this sector has been studied even more deeply. And we have summarized in tables like the one that you see here, the reach of all the Higgs factories that are projected these days, both in their initial stage and in an integrated over their lifetime stage. And the table that with the integrated reach of these machines can be found in the backup slides of this talk due to time constraints. The next very strong case is, of course, the exploration of the unknown at the multi-TeV scale, direct exploration of new physics, and the anomalies that we are going to see will have to be interpreted, but the interpretation will have to be validated. And the validation of that interpretation, as we know, with the discovery of the Higgs boson, needs to come through discoveries. And the multi-TeV colliders that will reach up to scales of 10 TeV will give us a pretty good chance of answering that question. At the same time, all these machines are not only they don't serve just one purpose. And as a matter of fact, the multi-TeV collider will also be in a way precision machines, and they will give us in particular a very important precision measurement, which is the measurement of the Higgs self-coupling, and maybe even tackle the distinction between the triple and the quartic self-coupling that gives us the shape of the potential. So moving to the EF vision, physics visions for EFs, no mass is about physics. It's not about planning in detail the cost and the time frame and everything. It's about vision with some idea of time frame in mind. So our vision is articulated in 3 steps, as we have 3 very strong physics cases. The immediate future of our vision is the high luminosity LHC. It is compulsory, it is mandatory, given the performance of the LHC and the potential of the physics case of the high luminosity LHC to complete the highest priority recommended by P5, in particular because the scene has changed quite a bit and has given us even stronger reason to complete the program by collecting at least 3 inverse femtobars of data. The US community have been strongly involved in this venture, and wants to keep being strongly involved. We think that is critical to the success of the high luminosity LHC. We have articulated our vision as the mandate that has been given to us in the next 10 years and after 2035. So in the first, and we have articulated that in blocks of 5 years, just to be a little bit concrete. So with this structure, we see for the next 5 years, starting in 2025, so not really the next 5 years, but the 5 year next to 2025, prioritization for the high luminosity LHC physics program, including auxiliary experiments that have been proposed. For the next 5 years, continuing this strong support, and after 2025, of course, support continuing the high luminosity LHC to the extent of the conclusion of archival measurements. The next step in our vision and the next component of our vision is the intermediate future. And we see for the realization of the EF physics program, the next 5 years to be not the next 5 years, but the next step in our vision. So the intermediate future to be any plus or minus Higgs factory, either in the form of a linear collider or in the form of a circular collider. All proposed facilities have a strong common core, and we think that at least one of them will have to be realized somewhere in the world. And what has emerged from SNOMAS is just, it is crucial, it is mandatory that we start a fast start towards this construction is emphasized for the health of the community, for to keep the drive and the enthusiasm and the education also of the early career physicists. For the next decade and beyond, we see between 2025 and 30 to establish a targeted E plus E minus Higgs factory detector R&D for US participation in a global collider. For 2035, support and advanced construction for this machine. And after 2035, begin and support the physics program of the machine. Finally, the long-term future in the EF physics vision is a multi-TeV collider. The physics case has been discussed before, and we see 2 options in here, either a 100 TeV proton-proton collider in the form of the SCCHH or SPPC, or a 10 TeV muon collider in the form of the proposed muon collider. They have overlap in the physics program. They have differences. They have different strengths. But both of these projects, they reach an unparalleled. They are unparalleled in terms of mass reach, precision, and sensitivity. And indeed, we stress again at this point that multi-TeV machine, they are also in a way precision machine in different ways from the plus and minus colliders. The main limitation we see is technology readiness, and because of that, we support a vigorous R&D program into accelerator and detector technology that we see as crucial. And for our 10 TeV and beyond timeline, we think that starting in 2025 to 25 to 30, we need to develop an initial design for what is called a pre-CDR of the first stage of the muon collider and support overall critical detector R&D towards energy frontier multi-TeV colliders. The next 5 years, we will see a demonstration of principal risk mitigation and deliver a CDR for the first stage of TeV muon collider. And after that, after 2035, they demonstrated the readiness for construction and delivery of the TDR for the first stage of a muon collider and wrap up funding and support for detector R&D OEF multi-TeV colliders. So we know that these enterprises are international enterprises, and one of these machines will have to be sited anywhere in the world. So the US community has always been involved in the international community and wants to stay involved in the international community. And therefore we advise that we strongly hope that the funding agencies would allow, with us, supporting strong R&D programs to the US community to do so. During this NOMAS exercise, the US community has expressed a renewed interest in bringing back the energy frontier to the US in form of the collider. And we see opportunities for that has emerged through the strong and very vital participation, in particular the young generations, to this exercise, submitting more than 40 contributed papers on muon collider studies and proposing and bringing through a whole new project, the C-Cube project. We see these opportunities for our community in terms of, in the form of either US-sited linear collider, plus and minus collider, or in the form of hosting a 10 TeV range muon collider and exploring the possibility of using the Fermilab side in the form of Fermilab side fillers. So summarizing the vision of the energy frontier in a nutshell, we think that it is essential to complete the high luminosity LHC program. It is important to start now a targeted program for detector R&D for Higgs factories. It is important to support an essential construction of a Higgs factory. And it is essential to ensure the long-term viability of the field by developing a multi-TeV energy frontier facility, such as a muon collider or hadron collider. And in these, our support goes to AF, CompHEP, IF, and TF, because their support is crucial to the realization of the energy frontier vision.
Thank you, Laura. Sorry, I have to stand here to chase you out. Our next speaker is convener of Neutrino Physics Frontier, Patrick Hoover.
One is yours. All right, very good. Good morning, everybody. First of all, I would like to thank the local organizers for running a very complicated meeting flawlessly. And I also would like to thank my co-conveners, and particularly the topical group conveners, which really had a difficult job during 2 years of COVID in Zoom meetings. Without their input and the input of the whole community, we wouldn't be standing here today. This is a very famous letter here, which starts with Liebe radioaktive Damen und Herren. I don't have to, read the letter to you, but what's remarkable is the date, 1930. So we're here 92 years later, and we still, know relatively little about the neutrino which Pauli predicted so boldly. I also will say that has changed too. Pauli was very ashamed of predicting a particle which he had no idea how to detect. That has changed. But in any case, so these are the science drivers for Neutrino Frontier, which are largely grouped into, can be grouped many ways, but sort of intellectually are grouped into two pieces. One, the properties of the neutrino itself, and then the neutrinos as a way to study other types of physics. And of course, the first question is, now that we have neutrino oscillation, we neutrinos have masses, but we don't know what the masses are. We know they're smaller than an electron volt roughly, but that's about it. We also would like to know whether neutrinos can be their own antiparticles. So that's the question of whether neutrinos have a Majorana mass or not, which has impact, for instance, on questions like leptogenesis. We also would like to know how the masses are ordered. What is the origin of neutrino mass and flavors? So the overarching question, we eventually would like to figure out, where are these numbers coming from we can measure, and maybe find a flavor theory in the process. And then sort of more specifically to neutrino oscillations, do neutrinos, antineutrinos oscillate differently? So that's the question of CP violation in the lepton sector. Again, sort of stipulated by the fact that the universe contains more matter than antimatter, so we still would like to understand the CP symmetries of our underlying theories. And of course, we also would like to discover new particles interactions. And of course, also neutrinos are a messenger of all sorts of interesting astrophysics and cosmology. Now, we are in a situation where a lot of our physics, which is at the core scientifically, is actually not supported by the high energy physics program. So in particular, neutrino mass, so direct kinematic neutrino mass searches and neutrinos double beta decay experiments are supported by nuclear physics. and they tend to be small and medium sized, certainly compared to any accelerator-based programs we have. And the other sort of science drivers will be addressed, not exclusively, but to a large degree addressed by Dune's phase 1 and 2. And Dune phase 1, by any definition of that word, is a large experiment. And the construction is supposed to sort of end around 2030, give a year or two. And then Dune phase 2, which will comprise 2 medium-sized detector upgrades and a large accelerator upgrade, but large at the very low end of large. It's right sort of between small and large. And the hope is to start construction for that in the early 2030s and finish that in the 2030 decade. There are many, many other smaller projects which contribute to sort of address these questions, but most of them have a small or vanishing US AGP contribution. All right. Sorry, that's the wrong direction. Here we go. This is our message. This is essentially the same slide I have shown on Friday. So we would like to have a broad program across timescales, sizes of experiments, and so on and so forth. And we would like to have a really deliberate process and ongoing support for this, and not sort of in this start-stop fashion, which we had experienced, and I think like from the last numbers a little bit. Of course, the completion of the existing experiments like the Fermi Short Baseline Program NOVA and so on is a very high priority. And the execution of Dune in its full scope are critical for addressing the NF science drivers. And the sort of phasing of Dune offers the opportunity to expand the scope of the Dune far detector. So for instance, you could imagine that one of the Dune modules becomes a very large dark matter detector. But that really requires R&D, and this R&D needs to be supported. We need strong and continued support for neutrino theory, both to sort of explore all the ways we can do interesting physics beyond neutrino oscillation, but also to support the core physics program across all scales in interaction physics. And of course, I think there are unique opportunities for the neutrino frontier to contribute to leadership for a cohesive AGP-wide strategic approach to DI and community engagement. I think we all share this goal across frontiers. We just need to find out how to best implement that. And I think we really have a serious discussion, which maybe doesn't even have to really wait for P5 to think about how to best do this. All right. So my task was to give you an overview of all the projects, and the problem is sort of outlined in this figure here. This is based on a community survey where the experiments sort of self-report, and it's not quite finished yet, but you see we're here at the dashed line. There's the laser here, we're right here. So we have a lot of experiments which currently are data taking. We have a lot of experiments which sort of are on their way to be data taking at some point, and then we have a whole bunch of ideas for the future. It's really impossible to cover these in the closeout, even if I had 120 minutes. Okay, that would not be easy. The one important thing to stress is that only very few of these things individually ever will rise to the level that P5 would make a recommendation, say experiment X should proceed under those conditions or something like that. So the only large thing in here, of course, is this one. It's Dune. All right. Okay, so now I will talk a little bit about the individual sort of science drivers. So neutrino mass measurements with Katrin, we have reached sort of 0.8 electron volts. Katrin has maybe another factor 4 in sensitivity in it. And this will happen certainly by the end of this decade. The idea is to go beyond Katrin, but if you really want to push significantly below 0.1 electron volts in direct mass measurements, R&D is of course mandatory. As Tim has said, cosmology will inform the sum of neutrino masses quite precisely. The current limits already are very, very competitive, and soon they will really go well below 0.1 electron volts, which is great. And this is complementary to direct searches. So we're looking very much forward to these results. Then, of course, the big one, neutrinos, their own antiparticles. So this here is, of course, the famous neutrino loss Devoped decay, where this is mediated by a neutrino mass term. But this can be mediated by a lot of other things which really have nothing to do with neutrino mass. So if we observe this process, figuring out what caused this process is certainly clearly the next target. There's a whole bunch of ton scales here in neutrinos Devoped decay experience at the start right now, and they will cover the inverted hierarchy sort of 10, 15 years from now. As I said, but this is essentially not a topic for P5 because that's owned by somebody else, nuclear physics. The question is, if you go beyond the ton scale, how we do that, that needs to be maybe reviewed. All right. Then the ordering of neutrino masses, there are many, many ways to go after that. In the near future, I think the most significant inroads will be made by Juno in China, which is a precision oscillation experiment, which apart from the mass hierarchy will really nail down oscillation parameters with percent level precision, which is going to be crucial for future unitarity tests, for instance. And of course, also atmospheric neutrinos, especially coming from things like IceCube, may also add information here. But of course, the real resolution of that question will come from Dune and Dune phase 1, which sort of corresponds to this magenta purple region, can do this with significantly more than 5 sigma throughout the parameter space. And of course, the goal is not to measure the mass hierarchy with 25 sigma, but to actually study matter effects very precisely. So, can do percent level matter effect studies. Hyper-K has some sensitivity coming from atmospheric neutrinos to that, but for that, they need to accumulate statistics, so it takes a while. That brings us then, of course, to CP violation, which is sort of the core program of these large oscillation facilities. So these are 2 different ways to show the sensitivity. Here they show 90 and 0, which are basically this point and this point for Hyper-K, and this is just shown as a function of the true value of delta. The sensitivities are very, very comparable. The systematics is entirely complementary. And since this is a very hard measurement, actually having 2 independent ways of measuring this is going to be crucial to making sure that we got it right, but also if you want to look for new physics, that gives you unique leverage to address that. Dune will be a staged experiment. This is sort of the mass hierarchy reach of phase 1, and this is the CP violation reach. And what's important is the mass hierarchy is a clear and quote easy goal for phase 1, so they can do this very well. But for CP violation, you get at most 3 sigma if CP violation is maximal. And of course, there's no guarantee it is. The current parameter space is still wide open. And so that's why you need phase 2, which covers half of the parameter space at 5 sigma, and will do precision physics for the other parameters. And this, as I said earlier, requires far detector mass upgrades, near detector upgrades, and the beam upgrade. And this shows you how the sensitivity in this case would evolve. Then we also have the potential to discover new things in neutrino experiments. And there are 2 ways to do this. One is by the operators like this one, where new physics directly somehow mixes with the neutrino. This is the neutrino portal to a dark sector. And you get this essentially by precision studies of neutrino interactions and neutrino oscillation. But as it turns out, as you can also look for new physics, which has nothing to do with neutrinos at all, because actually we make an incredible number of pions and photons in our neutrino beam facilities, which then can decay to dark sector particles or heavy neutral leptons. And at the end of this decay region, we have detectors which are uniquely sensitive to basically nothing comes in and you produce a spray of particles. And so in that way, neutrino experiments can, for instance, look for dark matter candidates. Then, of course, we also have neutrinos as messengers. After all, solar neutrinos is what started a large swath of experimental neutrino physics more than 50 years ago, which led to the discovery of neutrino oscillation. We have observed neutrinos from a supernova once. We'd like to make this a regular occurrence. And there are ways to do this. I mean, Super-K soon will start seeing the afterglow of all past supernovae, for instance. And we can also, look at the neutrino signal following gravitational wave bursts. Here we did not see neutrinos after this event, which also teaches you something fine. And here we have sort of a coincident neutrino with a gamma ray flare. So this is really truly multi-messenger astronomy. And neutrinos is a crucial leg of multi-messenger astronomy. Much of that instrumentation, however, sits in portfolios which are not HEP, but of course, physics-wise, we're very excited about that. Then, of course, we have an enabling program in neutrino interactions, and we need this at many energy scales. It's essential to the physics. This would be small experiments, and here the key is, of course, collaboration with theory and nuclear physics. And the fact that T, K, and Nova right now seem to get different values for delta could be exciting new physics. That could be also cross-section in systematics, and so this is going to be crucial. And I will say, especially for BSM searches, we need to control our quote standard model background. And so that to conclude, there are also synergies at the machine level as the physics level with many other facilities, like the forward physics facility at CERN, or maybe a muon collider R&D program will probably produce very nice neutrino beams. So to really conclude these are the science driver of the neutrino frontier. They really all belong together, despite the fact that the funding is cut up amongst many pillars. And maybe what's worthwhile to point out is that these two science drivers have seen the last discovering new particles, interaction, neutrino messages, have seen a significant growth in activity since the last snowmass. Well, after all, IceCube now has detected astrophysical neutrinos. We have seen gravitational waves. And of course, the LHC results have inspired a renewed interest in sort of low energy, weakly coupled particles, which essentially we have one. It's called a neutrino. And so, these things are very similar to neutrinos, and so it's natural to look for them in neutrino experiments. Thank you very much.
So this speaker is also and co-convener of the rare decay.
Okay, so can you hear me? Okay, so good morning, everyone. I am going to try to summarize the basic physics tenets of a very rich and complex frontier, the rare decays and precision processes frontier, just to name, illustrate the challenges of summarizing everything that we are about. And one definition which fits our work is that we are really a crossroad for the next high energy physics landscape. As you see from this plot, which summarizes the mass scale for new physics that we are exploring in our experiment, you see that in direct measurement in flavor, both in quark flavor, muon flavor, and then in the dipole moments, probe mass scales, which at the moment are not available to us in direct searches. Moreover, we have a strong connection with the neutrino frontier. The complexity of the quark coupling, as opposed to the complexity quite different of the neutrino coupling, gives us an avenue to perhaps explore other puzzles. And finally, we are exploring several interesting observables in the dark sector, which is linked to the still unsolved mystery of dark matter, another fundamental question that we have in the field. So here is the team. First of all, I have to thank my co-conveners, with which we had a lot of fun in the long hours of work, and then all the various topical group conveners, which really enabled us to put a compelling physics kit together. And also we have several white paper contributors, which are exceptional. Okay, so the big picture. Our goal is to develop a sustained and diverse and experimental program, well motivated by the P5 science driver, explore the unknown, new particles, interaction, and physical principles. And actually, we explore all these three facets with connection to the energy and neutrino frontier. However, we believe that we should be introducing a new science driver centered on flavor physics, aiming at uncovering the physics beyond the multifaceted patterns of coupling, sources of CP violation, and mass scale and nature of new physics with strong connection to the neutrino frontier. There are many experimental approaches, experiments investigating heavy and light quarks, charge leptons, precision tests of fundamental forces and symmetry, dark matter, and the dark sector. We strongly support the associated theory, phenomenology, and lattice QCD, which enables and inspires this very broad work. So here is our treasure hunt. We are investigating the origin of flavor generation and quark and lepton mass hierarchies. We want to exploit flavor decays as precision probes of all the sector of the standard model and windows to new physics. We want to understand the motivation underlying discrete standard model symmetry and mechanism for their breaking. We want to investigate the origin of baryon and lepton number violation and the connection with the baryon asymmetry of the universe. And finally, we want to map the wealth of conventional and exotic hadrons already discovered and on the horizon into organized multiplets of QCD bound system. Here is our treasure map. So we have a portfolio of accelerated dark sector experiment, charge lepton flavor violation experiment, a high precision experiment with special focus on beauty and charm decay, experiment studying discrete space-time symmetry, symmetry breaking, electric dipole moments and baryons, and baryon lepton number violation. We are sustained by phenomenological and lattice QCD theory effort, innovation in instrumentation, and innovation in computing and accelerator physics. Disclaimer, now I will walk you through a few of the physics topics that we are pursuing. I just want to give you a flavor of physics, a more complete and thoughtful picture will emerge in our report. So let me start by speaking about heavy flavor, the next chapter. So this is a picture of some kind of idea on deviation from the standard model, which are driven by a bunch of anomalies which have been discovered in the decays, which illustrate kind of the basic mechanism with which we are trying to search for new physics, just examining the interference between suppressed standard model diagrams and diagrams in which new particles manifest themselves. So more precisely, precision measurement of weak decays of heavy flavor hadrons can further our understanding of fundamental interactions and baryon asymmetry. We have seen these tantalizing hints of new physics. In the next 10 to 20 years, we see an unprecedented development of synergistic programs in E plus E minus machine and proton-proton machine. And this is shown in this picture, which gives you a landscape now. And going into the future, so you see that LHCb has a path to several upgrades, and so Bell 2 has identified a long and Weierstrass program, and further down the line, there is some idea of utilizing future facility for flavor physics, and similarly there are tau charm factory. Okay, so next we want to explore lepton flavor universality violation. There are several tensions which are emerging, so not only the one that I talked about, but there are also the G-2 asymmetry and a few other things listed here. Now, there are complementary studies in light meson decays, and this program is carried further by some experiments which are planning to utilize rare pion and data prime decays as a leverage toward accomplishing this new physics. Next, we have a broad research focused on precision tests of fundamental properties and symmetry. One of the key points, as shown in the first slide, is measurements of the electric dipole moments. And these allow new physics up to unprecedented TV scale. There are a variety of approaches. And now there is a new HEP opportunity utilizing storage ring proton EDMM measurements. There are the magnetic dipole moments, focusing on the muons, which allows search for physics beyond the standard model at the few TV scale. And again, sustained by a large theory effort that you learn about. And then there are precision experiments of basic symmetries. So a couple of words on charge lepton flavor violation. Again, this is motivated by the fact that we have neutrino masses. We have a variety of new sector, and here you see how the precision of these rare decay probes evolved over the years. And here there is a new initiative which has been proposed in the context of our frontier, a new muon campus at Fermilab, which should provide order of magnitude increase in sensitivity for the various rare muon channels which are of interest. It can also dark matter experiment, and some of the technical challenges are synergistic with the muon collider R&D. A complementary approach not related to flavor is the dark sector. The existence of dark matter motivates a dark sector, which is basically connects through a portal interaction to the standard model that we know and love. It is a compelling possibility for new physics, which influences a lot of the physics that I have discussed. And the dark sector are generally weakly coupled to standard model matters and can naturally have MEV to GeV scale. Here is a snapshot of the initiative as it is currently ongoing. So there is a possibility of exploiting the capability of multi-purpose experiment, BEL2, LHCb, to explore this sector. There is a promising start with the dark matter new initiative, which should be expanded upon. And again, theory effort is really crucial to pursue this program. Here is a list of the experimental facilities proposed. So you see that there is a lot of interest and a lot of great ideas in this sector that need to be explored. Okay, so now I will read our main recommendation. So the first one is that the physics of our frontier needs a new P5 driver to be represented adequately in the HEP landscape, broadly identified as the physics of flavor. The LHCb and this upgrade 2 and BEL2 are part of a portfolio of exciting physics opportunity that explore a vast array of new physics in beauty and charm decays and in rare tau decays. In addition, they investigate the pattern of bound states as manifestation of QCD in the non-perturbative regime and contribute significantly to the exploration of the dark sector. A portfolio of accelerator-based dark sector experiments that are well motivated, unique and affordable should be considered. Experiments investigating charge lepton flavor violation and lepton number violation in the muon sector are an integral component of our exploration of mass scales currently enriched with direct detection. R&D toward the new muon program at PIP2 should be given strong consideration to enable a concrete proposal for the next P5. A portfolio of experiments of different cost and time scale are integral part of our physics program. They include EDM measurements, including storage ring EDM, and we lost any, and experiment exploiting AMO techniques. Experiments leveraging on light measurement decays to uncover physics beyond the standard model, including anomalies and portals to the dark sector, are important to our program, and contribution to experimental studies of rare kaon decay should be encouraged. We need to support the theoretical efforts that inspire and elucidate the implication of our experimental findings. And then I would like to conclude with something which is inspired and illustrated by one of my other interests, which is the theater. So you know that there is a play which says that everybody is connected by at least less than 6 degrees of separation. I think that we are all connected by much less than 6 degrees of separation. So I put our frontier in the center, and I would like to highlight connection to the other physics frontier, the energy frontier, neutrino frontier, and you saw also in the talks by the previous speaker how strong the connection are. Cosmic frontier, actually it was his previous speaker too, so. But also we would like to highlight the connection with the instrumentation frontier. I give you a few examples of the things which connect us. And I think it's really important that the instrumentation frontier connects as a community for all the physics topics that we are highlighting. Computational frontier, we have massive data which need to be stored and processed in real time and then interpreted with the use of artificial intelligence. And community engagement frontier. I think that there are several leadership opportunities for young scientists, and we want to devote our attention to training an inclusive and nurturing environment, and we want to have a connection with industrial partners. And let's see, and then last connection that I want to make is that in addition to the HEP community, some of our experiments are funded by nuclear physics and AMO communities. So also opening up different experimental communities to try to figure out big questions that we have about the micro world is very important. And I conclude here.
Thank you, Marina, for this very nice talk. So we move to our last but not least frontier. theory frontier, and this will be presented by convener Aid El-Kadr.
Can you put the captions there? Okay. Thank you very much. It is my pleasure to give our summary of the science highlights from the theory frontier. My co-conveners are Nathaniel Craig and Csaba Csaki. And of course, we had a lot of help. So let me get started by just giving a brief impression as to how we think about high energy theory. We have organized our report along three interconnected themes in fundamental theory, phenomenology, and computational theory. These form truly a interconnected scientific ecosystem. And this, this circle is also meant to represent the series of virtuous circles that exist where insights from one area feed into another area and come back to provide more profound insights. And there are examples of that. Theory, as Marcella already said, is, I like her wording, is the glue. It unifies all of the frontiers of particle physics and is essential to all the experiments. It is central to the motivation, analysis, and interpretation of the experiments, as was already emphasized by all the previous speakers. I'd also like to emphasize that it is responsive. Theorists are responsive to when they're exploring and proposing new directions when the experiments guide us so. And in turn are also, there's a track history of proposing and guiding new experiments and or developing new analysis tools to the changing landscape. And so theory then also lays the foundations for future experiments. There is been a lot of discussion also of the importance of machine learning and artificial intelligence and quantum information, and you will see that woven through my talk as well. So theory does incorporate new perspectives and also new technologies in computing, for example, to extend the boundaries of our knowledge. And especially in fundamental theory, but not just, theory advances our understanding of nature, even when experiments cannot reach it. And finally, theory also connects outwards with a lot of the other fields, obviously gravity, cosmology, astrophysics, nuclear physics as well, condensed matter, AMO, and mathematics. And I've already mentioned computing here. So with that in mind, then I'm going to organize the science highlights along the three themes, starting with fundamental theory. And I might start by saying that today's deep insight into a fundamental aspect of theoretical structures that might appear obscure to people who haven't really thought about this becomes tomorrow's essential tool to make progress in phenomenology and maybe even connect them to experiment. And there's a rich history of that. I would like to say here that the timelines for this in some cases are getting shorter, in particular with including quantum information in the considerations. There is a very direct pipeline between fundamental theory, but it's not the only area, and phenomenology and computation as well. So a interesting new development has taken place. This is in the area of black holes, quantum gravity, string theory, where holography, studying ADS-CFT equivalences, has been, of course, a gold mine, including entanglement entropy and other entropies as well. That's the quantum information part, then led to some very interesting insights, which can be understood as providing quantum error correction, where quantum information in the bulk is then represented redundantly on the boundaries, and that's the correction. This is yielding important new information on the black hole information paradox as well. Effective field theories have been, for eons, have had a very important role in high energy theory, organizing the scales and allowing us to compute things without needing quantum computers already. There's a long history of effective field theories that non-relativistic effective field theory, HQET, the standard model as an effective field theory, and new applications using similar ideas for new systems in dark matter and gravitational waves and condensed matter, new developments in standard model effective theory, SMEFT, yielding new applications. But there's also been quite a bit of work in expanding the theoretical foundations for effective field theories, considering principles such as naturalness, unitarity, analyticity, and causality, and other symmetries, that is providing us new tools to study quantum field theories with. In the study of conformal field theories and fundamental aspects or formal aspects of quantum field theories, the bootstrap has been a gold mine, and there are quite a few different versions of it where one uses symmetry and other principles to constrain or determine a physical quantity without relying on underlying Lagrangians necessarily. This is kind of shown schematically like here, and there has been a very recent work on that basically provides a bootstrapping perspective in quantum gravity that might yield more insights in quantum gravity as well. And amplitude methods have had an important history inspiring multi-loop calculations already for collider phenomenology, and also advancing the state of the art in just general quantum field theory considerations. Recently there is the insight into double copies, whereby gauge amplitudes are related to gravity amplitudes, and then one can use the apparatus that has already been developed in amplitude methods to turn this into observable templates that can be used for black hole collisions, for example, for gravitational wave phenomenology. In phenomenology, I want to start with precision, and Marina has already talked about the power of precision in flavor physics, and that, of course, when we have precise experimental information, we see now some anomalies because there are theoretical calculations, precision standard model theory, that are commensurate, and these are revealing some of these anomalies. A new one that you maybe haven't heard about yet is the Khabibo anomaly, which concerns the first row CKM unitarity test, which appears to be failing and has inspired further studies. In Also in precision is the precision standard model theory for collider physics, which has provided very precise predictions for Higgs decays, for Higgs decay rates, which is of course very important for us to understand the nature of the Higgs boson, and that will continue. Also for collider physics, there is a concerted effort to extend the calculations towards 3-loop next to leading order precision, which carries the promise of having a whole suite of standard model predictions at the less or at 1% level, providing exquisite tests from collider experiments. There is a whole program here. It's not just computing the loops, which by themselves, then those computations are, as I just said, also requiring a fair amount of computational theory and mathematical insights. There is advances and pushing on further developing Parton distribution functions and generators to match this overall precision. So that's a program to answer to the collider physics program. At the same time, in collider phenomenology, there's been a really beautiful work in illuminating the jet substructure, also using machine learning for that, developing new observables, things like multi-point correlators, and as I already said, leveraging those new technologies and pushing these methodologies towards actually deeper understanding of the underlying fundamental theory. You might not have realized that collider phenomenology can potentially, with exploring the connections, could potentially give us insights into the nature of confinement. It makes sense if you think about what comes out of those collider experiments, but the structures are so complicated and the theoretical developments are so beautiful that is a very interesting promise. In beyond the standard model building, the shifting landscape has inspired theorists to search out new paradigms, think about hidden sectors, new symmetries, split spectra to understand electroweak symmetry breaking, as well as also baryogenesis and leptogenesis, of course. And this is yielding interesting new search strategies and constraints. I'm getting close to being done. As I already pointed out, theory is also not shy to make use of new technologies, and nowhere is the interplay between new technologies, experiments, phenomenology stronger than in the area of dark matter detection, where new quantum sensor technologies are being proposed for discovering new physics and also dark sector particles. And that very beautifully fits into the landscape that Tim described as delve deep and delve wide, which was put together with the help of theorists to provide both targets of importance and broader search strategies and proposing new experiments, as I said here, that are enabled by these new technologies. And of course, also connected to Tim's, to the cosmic frontiers mantra of delving deep and high is the explorations in cosmic frontier connecting to inflation and dark energy, which then connects fundamental theory and computational methods, simulations and observations all together. In neutrino theory, there is the challenge of understanding where the new physics scales lie and taking all of the possible information and condensing it. And then there is the other theory challenge, which is to provide precise predictions of the neutrino nucleus cross sections across all of the energy scales in the standard model and beyond. And this requires a broad program that combines expertise from nuclear theory, effective field theories, lattice QCD, perturbative QCD, and actually also generators and simulation. And this is being launched. So this is another programmatic effort in response to the experimental program, as the other programmatic efforts that I already described. Then just a few words on computational theory. Lattice QCD is one of the flagship areas in computational theory, having long provided now very precise determinations together with experimental measurements for alpha S, and pushing towards a lot more complexity, attempting to compute X-dependent PDFs, also nucleon EDMs, and first calculations involving multinucleon and light nuclei matrix elements. There's also a flourishing program of using lattice field theory simulations as a numerical laboratory to learn things about different strongly interacting theories that connects back to fundamental theory. The interest in quantum computing and quantum simulations on NISQ hardware was already emphasized in plenary sessions throughout here. There's been a lot of progress that has been described, and the results are really intriguing, and will bear fruit in the decades to come. I think I'm just going to skip over the machine learning, just to say that it is infusing many areas in high energy theory. So this is my last slide. Csaba, Nathaniel, and I would like to thank all of our topical group conveners who have reached out and taken all of the white papers that were submitted to the theory frontier. This is an impressionistic number. The true number is probably larger, and to help us then compile, condense everything into the theory frontier report with these science highlights. We also want to thank our liaisons, and most of all to all the theorists, and in some cases also experimentalists, who contributed to these white papers. One last word that I wanted to say is that some of the topical groups, some of the highlights that I showed you are part of programs, and we can expect programmatic improvements that address the needs of the experiments, and some go into creative directions that are sure to surprise us. Thank you.
Thank you, Aida, for this tour de force. You managed to do worse than me in timekeeping, which is a real challenge. So.
But I had fewer slides.
Okay, so thank you to all the speakers. And I think now we will invite them to come to the stage. And all of them, please keep, I will sit here to keep 6 feet or whatever it is, and you try to do your best.
Marcella, if you stop the screen share, then people will remember I'm here.
Sorry? Okay, so I am told that we only have 15 minutes, maybe 20, 15, no. Shekhar says no. Okay, we only have 15 minutes, so I will directly open the floor and keep my own questions for the background. So please, I would ask you to raise your hand so that someone can run and give you the micro. And you can ask the question to one of the speakers or to Tim sitting there as on the background. So please, wake up.
Hi, this is Rick Yoshida from Argonne. This is not really a question, but more of a, this is a comment more than a question, but this goes to the energy frontier. So I'm not an accelerator physicist, but having followed advanced acceleration since 2015 pretty closely, it seems to me that there are so many uncertainties in that field and how it's going to go, that it's not really wise to pick a particular technology to go 10 to 10 TeV. So I would suggest that, I mean, I think it's a very good goal, but I think we should really back off a little bit on specifying what sort of collider we look for.
So I'm not sure, I couldn't hear extremely well, but I think your question was that there are uncertainties that are not only related to technological developments. No, then you have to repeat it, I'm sorry. Maybe you can just for a second lower your mic.
Sorry, I know it's very hard to hear on that stage. So my comment was that it's, there are many uncertainties in the development of advanced accelerator technologies. And we are not, I don't think we're at a stage to say that we would like a muon collider to do a 10 TeV E plus or lepton collider. I think we should keep that option quite open.
Well, I think this is part of the studies that have been developed mainly by the accelerator frontier. And you hear more tomorrow about these facilities. As you have seen, there is a lot of part of our vision is also supporting the program for further studies. It's not done. We're not ready, shovel ready right now, although some of them are pretty close to that, in particular for E+ E- machines. So I wouldn't be so pessimistic about saying we are not ready. I would be pretty optimistic about the fact that there has been incredible progress, even during the 2 years of our work. And clearly that doesn't mean that there are no technological challenges, but they are being addressed.
Via Papadimitriou Fermilab.
It's really difficult to hear. It's impossible to hear.
So in case we miss the Higgs factories in the time scale we are planning for them, is there a good reason to insist on having them later than currently planned? Or we could accomplish the goals we want to accomplish pushing for the high energy colliders like, I mean, the muon collider or the FCC, etc.
Well, that's a very good question. And it's something that we have, of course, thought about, although at that point, you really have to investigate so many possibilities because the timeline is not really under our control. It depends. I think, as I said, that the multi-TeV colliders, that they also can do precision physics. But I think the connection with the staging of these machines is pretty crucial. It's pretty crucial to have them now as soon as possible, let's say. So it will have to be reevaluated depending on what comes out of the high luminosity LHC in between. It is very hard to give an answer now saying we can skip them. At the moment, we don't think we can skip them because they bring some fundamental measurement that are unique of an E+ E- machine and that have not been demonstrated to be still in the realm of, for instance, a mu+ mu- machine. So more studies will have to be done. And definitely at the moment, we think that it will be very important to have that stage. Also because it is not clear that if they are not, if we don't match that deadline, we'll match the next one. So everything can be pushed so far in the future that at that point it's hard to judge now.
So I was wondering, can one tune the energy of the high energy colliders so that one can accomplish some of the things that we would accomplish with a Higgs factory? In a sense, instead of going to a 10 TeV muon collider immediately, could you start at lower energies? I mean, are there intermediate solutions?
Well, this has been looked at, but you'll hear more about this tomorrow. We have considered also briefly the case of a mu plus mu minus Higgs factory, for instance. And that seems to be a completely different technological problem that is very hard to solve at the moment and propose at the moment. Now, staging the stage of a 3 TeV muon collider is being considered before the 10 TeV. And there too, it's a matter of a much farther future with respect to what we think is realizable now with any plus and minus machine, and not a complete equivalent program.
Yes, there have already been a number of questions on the Google Doc that the conveners have already been answering, so thank you for that. There's one for Patrick that I wanted to read out, which I will summarize as, could you please explain the complementarity between Hyper-K and Dune and how that plays into the phasing strategy? What will we learn over what timescale, and how might that affect the program?
All right, that would be a whole talk in itself to do really well. So the real complementarity between the two experiments fundamentally comes from the fact that one measures at long baseline with a large matter effect and a wide spectrum. So you really map the oscillation pattern across sort of one full oscillation. And you do this with very significant matter effects. That's Dune. On the other hand, you have Hyper-K, which is has a fairly narrow band beam, so it's measuring only a tiny fraction of a full oscillation phase, and does this with nearly no matter effect. So that has is important because the systematics is going to be very different because the energies are very different. So all your cross-section systematics is quite significantly different. Also, the targets are different. So in that sense, this gives you a very robust system of two measurements. And just for example, T2K and NOVA fundamentally have never agreed on any number out of the gate so far, because it turns out that even at this level, and these experiments are still statistics limited, systematics seems to be already very important. So that's one just pragmatic reason. Is the two experiments I think are needed to really be sure that we get this right. Physics-wise, the difference between very small matter effects and very large matter effects gives you a real great lever arm if you want to find new neutral current-like interactions the neutrino has. You can only find these really well in oscillation. This is a modification of the matter effect. In that case, sort of Hyper-K would serve as the control with no matter effect, so it establishes sort of the standard model value, and then Dune can measure sort of on top of that the new physics. That's sort of in a nutshell. Then, of course, for astrophysics, in the case of a supernova, Dune and Hyper-K measure completely different neutrino flavors, right? Hyper-K is antineutrino, electron antineutrinos, Dune is electron neutrinos. And if you look at the exciting physics of supernovae, collective flavor conversions and stuff like that, you really need to get every flavor channel you can, especially since a galactic supernova is a rare event. So you want to be prepared for that. And you can go on indefinitely. Now, in terms of timing, we always wish we were faster than we actually are. That's just, I think, a given for the field, especially in the United States. I think we have unique challenges structurally, which make it hard for us to stay on time compared to other regions in the world, which come from outside of AGP. I mean, an annual budget cycle is just not very well adjusted to 20-year projects. That's just an observation. But the point in science is not to be the first, but the point in science is to get it right. And I think that's really the focus. What Dune phase 1 will unequivocally do, and will be also first, if that's something you do care about, is of course a precision measurement of matter effects and determination of the mass hierarchy.
I have another question for Patrick. Neutrino people talk about the unitarity tests of the PMNS matrix, but as if it were a thing, but it's not a thing because there are too many entries that we can't independently determine. For example, we don't have tau neutrino beams, which are needed for some of them. What are the limitations here? Can we really test that the PMNS matrix is well constrained? There are bounds, but what can we fill in?
Okay, that's a very good question. The way to do this really, so first of all, yes, we don't know how to make tau neutrino beams, but nature does. So we don't have to make tau neutrino beams. So atmospheric neutrinos coming from, the other side of the planet, that flux is half tau neutrinos thanks to neutrino oscillation. The trick actually is not so much that we can't have tau neutrinos in a beam because oscillation provides them for us. And for instance, the Dune beam, once it reaches South Dakota, has a very large tau neutrino component. The real challenge right now is we need to learn how to detect tau neutrinos. And that's, for instance, where things like pixelated argon with very high resolution will make a real difference. And so actually, I'm quite optimistic that as Dune, progresses, we will actually learn how to reconstruct tau neutrinos and get a real handle on the tau neutrino column, if you would like, for the unitarity tests. The precision in the third family, like in all other flavor studies, always will be worse than for the other two families, but I think it's not a hopeless endeavor.
Thank you, Patrick. Last question. We have another online question.
So one of the questions on the Google Doc that we've discussed at Snowmass this week is the need to reemphasize or perhaps rebalance core research funding in our program relative to projects and operations. And I'm wondering if any of the conveners would like to comment on that.
Aida, would you like to comment on that?
On my slides, you might have noticed the P5 logo with a yellow pentagon inside and a brown circle. I took this from Jesse Thaler's beautiful talk on the frontiers of phenomenological theory. And the point of the yellow pentagon inside is exactly that the enabling that the theory as one of the enabling topics, but also computation and operations and research activities must be supported throughout all of the frontiers. So one of the things that Nathaniel will say will be that in the second panel where we discuss this a little bit more will be that we need a balanced program of research and projects.
Anyone else would like to say something?
So in a sense, I think that
team. Then we go to team, please.
I think that perhaps we can broaden the concept of projects. So, I mean, there are these big facilities and big experiments, but then, for example, another thing that can be thought as a mission of the laboratory is also to be centers in which the theory, in computation and instrumentation, which is relevant to the field as a whole, can be hosted. So perhaps I think that the line should be blurred a little bit, but with evidence to the things which are not generally considered projects.
Thank you, Marina. Tim?
Thank you. Yeah, I'm not sure I'm very comfortable with blurring lines, but I want to echo things that Aida said and point out actually that question came itself from somebody in the cosmic frontier, where we definitely see the same thing, that while we have to build, top-notch facilities and projects, we also have to actually do the research to get the science out of them. Thanks.
Anyone else would like to say something? You too? No, okay, we all was said, okay, yeah. I think we all agree that it's important, the funding in research, to make the funding in projects and operations worth it. We are done, okay. They are telling me that, so like when you go scuba diving, sober. Okay, so thank you very much, everybody, for being here, and I invite you to come back soon.